graphical verification of the conservation of mechanical energy. That is, kinetic energy plus potential energy is constant for a freely falling body. Okay. Now, here, so in that case, we have observed that at the height from where the body has been dropped, if it is at a height of h, we find that there we have maximum potential energy. In between, we have the potential energy as well as the kinetic energy, but the total energy remains as mgh. And on the ground, we again found that the entire of the potential energy got converted into your kinetic energy, and as a result, we observe that this is all. So at the ground also we find that the potential energy remain. Conserved. Okay. Now, in the same process, we were trying to show you the graphical representation of the energy conservation. Now, towards the end, the class ended because the time was up. So I'll just start with that graphical representation, and only one portion more is left. That is the application of the principle of conservation of energy to the simple pendulum. In case if you have a problem, Mayank, I had given you the answer. Okay, I'll once again and give you the answer to your question. Actually, principle of conservation of energy is not only one energy which has been created. Okay, there are many things or many work which has been done along with this, and in different era. It started from way back from 553 BC. Okay, in the Middle of Thebes. So, but that was not in the same condition. Okay, so then we have the conservation of mass. So various scientists, philosophers of their own time tried to put this into the conservation of energy, and finally it was being given by a French scientist, what we are studying now. Okay, that was first been propounded by the French scientist or philosopher, you can say. Her name was a bit difficult to pronunciate, but I'll try. Chariot. So I had given this answer in your group also, you can go through. Okay. So we were discussing about this, and as I told you, that today we will represent the graphical representation, although we have done it before also. I'll just explain you. So here we were drawing the graph which was representing. So we have taken two axes. Along the x-axis, we represent the height above the ground. And along y-axis, we represent energy. Now, in case of your mechanical energy, the total mechanical energy is considered to be as mgh. So this will represent mgh. In between, it will represent half mgh. Okay, this is your this is your ground, that is position C. Halfway we consider it as B, and the complete height as A. Now, if I consider the potential energy, all right, so the potential energy increases as the height increases. So from ground, as we move to height, this will be considered as h by 2, and this will be considered as h. Okay, so as you increase the height, you will find that the potential energy is going to increase. Now if I represent the kinetic energy, so the kinetic energy is maximum at the ground and it will be minimum at height h. Alright? So in between you will have P is going to represent somewhere h by 2. This is representing h by 2. Alright? So as the height is in as the height is increasing, the kinetic energy is going to decrease. So, but throughout this, the total energy remains conserved. Okay? Now, this will represent the total energy. This will represent the potential energy, and this will represent the kinetic energy. Okay, so this is a graph, maybe a slightly. This is actually, this position should be at h. This is the condition at h. Okay, so this will go like this. Here, because of the drawing not very perfect. So this is your graph. I hope the graph is clear to all of you. We are coming to the principle of conservation of energy to a simple pendulum. Now, application, we are applying this principle of conservation of energy to simple pendulum. Now, in case of a simple pendulum, we all know that if I consider this as a simple pendulum, so it has got a bob of mass m. Let us consider the mass of the bob as m. Let the bob be at its mean position A. A is considered to be as mean position, and then we take it to one side. Right? The two extreme positions are B and C. Now, when the bob is taken from A to B, if you observe, the bob is going to cover certain height. Let this height be h. It rises by a height h. Natural practice also you will find if you are taking the bob from the mean position to the position B, it rises by the height h. Now, as it rises by the height h, so here we'll start the oscillation from B, and then it will go to the other end C. So while it is going to the other end C, again here also you will find it is going to rise by a height h. Okay, so if we consider that force of friction or the resistance between the bob and the air is considered to be uh, zero or negligible, or if we do not consider the force of friction, okay, in that case, the energy in this is also going to be conserved. Now, at position A, or rather at position B, since it gains a height, so the potential energy will become mgh. We all know that at this position, extreme position, the velocity becomes zero. As a result, the kinetic energy will become zero, and hence the total energy at position B will be your mgh. Similarly, at position A, when it comes back from B towards A, okay, it starts reducing its height, and this potential energy starts converting into kinetic energy as the bob gains the velocity, and at position A it will have the maximum velocity, which can be calculated or which can be given by the formula v is equal to under root 2g h. Okay, this is the velocity at A. Now, at A, the potential energy will become zero, whereas the kinetic energy, the entire of the, now, when we say potential energy becomes zero, it means that the entire of the potential energy will get converted into kinetic energy, which will be mgh, and as a result, T will be equal to, again, mgh. Now the bob rises to or moves to the other extreme C, and again it is going to gain its height. As the height is gained, we find that the velocity will be decreasing, because at the extreme position, the velocity for a very short moment, the velocity of the bob will become zero. As a result, at C also you find that u will be equal to mgh, k will be equal to zero. As a result, T will be equal to mgh. Hence we can say that hence we can say that the principle of conservation of energy is being applied over here also. The energy remains conserved during the oscillation of the bob from one extreme position to the other extreme position, and hence we can say that principle of conservation is obeyed here also. The point which we have to take care in this case is that we have to consider that the obstruction or the resistance with air of the bob is going to be zero. Okay, or in any case, wherever we are applying the principle of conservation of energy, we consider that the energy degradation or the dissipation of energy due to the resistive forces like friction and other is considered to be negligible. So you can say that if we carry out the oscillation of simple pendulum in a condition where we have energy zero, for example, in vacuum, then we can say that the principle of conservation of energy is applied. For theoretical purpose, we consider that it is negligible and it will be applied. So in a numerical or in a question, if it has been said, okay, so we will be doing all the calculations for giving out the reason, considering that it obeys the law of conservation of energy and there is no loss of energy during the energy conservation. So I hope this is clear to all of you. If you have a question, you can put it, can ask through chat. And v is under root 2gh, so otherwise the velocity is not zero. Height becomes zero. No, actually, when the bob is coming from the extreme position, say from position B to position A, okay, the potential energy gets converted into your kinetic energy. In other words, the body comes from the higher position to the lower position, and as a result we find that its velocity will be increasing. Okay, so as its velocity increases, therefore this will be this will not be zero. Now from A to C, when it is reaching, you will observe that its velocity will be decreasing, and hence by the time it reaches to height h, okay, its velocity will be zero. We are applying, okay, we are applying the concept that the entire potential energy is getting converted into your uh, kinetic energy. So I'm just showing how we are getting this under root 2 square root 2 gh. Now, actually what we are trying to do is, when the bob reaches to from B to A, okay, at B we have the potential energy which is equal to mgh, and we consider that the entire potential energy is converted into your kinetic energy. As a result, K is equal to half mv square, we know, and U is equal to mgh. This we have done it in the last class also. So from here we get V square is equal to m will cancel. This will be 2gh, and V will be equal to under root 2g. The velocity will become under root 2g. This is the maximum velocity which the body will be attaining when it reaches to A. So from B till it reaches to A, okay, its velocity will be slowly increasing, and at A its velocity will become 2 under root 2gh. Okay, and this is basically on the concept of conversion of entire of the potential energy into the kinetic energy, considering that there is no loss of energy taking place. So I hope this is clear. Yes, definitely you can get it. What is the question and why you are worried? Wherever the gravity is zero or negligible, see, entire of the activity, the gravity increases, negligible, or it becomes zero, that will be different. The entire behavior is going to be different. Okay, so they will also be behaving in a different way. For example, you simply you are able to eat a normal food normally. Okay, we even don't feel the experience of the gravity. But the astronauts who are going into the space, you don't find that they eat the normal food, because whatever is happening, the food which we are engulfing, or it is going into our stomach, that is because of the gravitational pull on the food. Similarly, on the other activities. So we'll discuss this in the next portion, or maybe in the group. Okay, we move to the next portion, that is numerical part. Okay, exercises, you will be doing question number 2 from exercise 2C, question number 2, 3, 5, 7. Okay, now we'll start with the numerical. There are a few numericals in this. So we start with the exercise 2C, numericals. Okay, the first one. See, entire of this, the base behind all these numericals is your law of conservation of energy, which says that your energy is, one form of energy is getting converted into another form. And most commonly, here we are going to deal with the conversion of your kinetic and potential energy. Okay. So the first question says that a ball of mass 0.20 kg, so the mass of the ball is given as 0.20 kgs, is thrown vertically upward with an initial velocity. Velocity is given as 20 meter per second. Okay, calculate the maximum potential energy it gains as it goes up. So we have to find out U. Now, maximum potential energy it gains. So U max we can write down for our understanding. U max we have to calculate. Now, definitely a ball is at the bottom and we have thrown it and it reaches to a maximum. So here, when we are throwing, the moment it leaves the ball, it will be having the kinetic energy. And this kinetic energy at the maximum height will reach and will get converted into your potential energy. So U max we can write it as equivalent to K according to conservation of energy. I'm writing down in a small, you will not write spaces. Okay, according to the law of conservation of energy, U max will be equal to K, and K is given as half mv square. That is half into m. You can even write down as U square. Initial velocity it is saying that. So we'll use the symbol U. So here also we are going to use the symbol U only. So half mass is given as 0.20 into U square, 20 square. So this comes out to be 400 and this will be 0.1. So 400 into 0.1 will be your 40.0. Energy unit is joules. It comes out to be 40 joules. I hope this is clear to all of you. Yes, they will adapt according to the environment. Till now, we have not found any life on anywhere where the gravity is 0. They have different type of life at all. I hope this question was clear to all of you. Now we are moving to the next question number 2. It says that a stone of mass 500 grams is thrown vertically upward with a velocity of 15 meter per second. Calculate the first part is potential energy at the greatest height and the kinetic energy on reaching to the ground and the total energy at its halfway point. So mass is given as 500 grams. This we convert it into SI system. So we get it as 0.5 kgs. Okay. The velocity is thrown vertically upward with a velocity of 15 meter. So initial velocity is given as 15 meter per second. Calculate the potential energy at the greatest height. Now potential energy at the greatest height, that is U max, will be equal to K. That is the maximum K it will be having. This will be equal to half mu square. This will be equal to half, mass is given as 0.5. Please, substitution of value is very important. This step is always very important. So whenever you are solving the numerical, always do not forget to show the substitution of the values. Okay, how simple it is. Now on solving this, we get it as, this will be 225 multiplied by 5 and then divided by 2. The answer comes out to be your 56.25 joules. Alright, so this is your K max. Now the second part, it asks you the kinetic energy on reaching to the ground. Now keep in mind this, what it is saying. It is saying a ball is thrown up. So here we have to find out. And then this ball comes down. Okay. So here we have to find out U and here we have to find out A. So definitely when the ball comes down, considering that there is no loss in, so this is your A part. In B part we get the kinetic energy will be equal to your, that is on ground. This will be equal to again your potential energy maximum. This is equal to 56.25 joules. Okay, so I hope this is clear to all of you. Now C part. C part, what it tells, it asks you the total energy halfway point. Halfway. So in between, that is in middle, U will be U half plus K half. Half here represents, that is halfway point. So U half and K half means U half and K half, it means that T will be equal to 56.25 upon 2 plus K half will be again 56.25 upon 2, because halfway, half of the kinetic energy will get converted into potential energy, half of the potential energy will get converted to kinetic energy. So halfway it will have both the energies, kinetic energy and potential energy. And keep in mind, this is strictly saying that halfway, that is why we are dividing it by 2. And as a result, if you solve this, you get it as 56.25 joules. Okay, so what you find over here is that it shows you that the interconversion of your kinetic and potential energy, and throughout, wherever you find, the total energy is always going to be constant. I hope these two questions are clear to all of you. If you have a question, you can put them in the chat. Okay. All right. So we move to the next question. We come to question number 4. Question number 3. mass kg is allowed to fall freely from rest from a height of 5 meter above the ground, taking g equal to 10 meter per second, the potential energy possessed by the ball when it is finally at rest, the kinetic energy, and what happens to the mechanical. Mass is equal to 2 kg, falls freely from rest. From rest means initial velocity will become 0. From a height, h is equal to 5 meters, and g we are taking it as 10 meter per second square. So first part, potential energy, U will be equal to mgh. M is 2 into 10 into h is 5. That comes out to be 100 joules. Okay. Kinetic energy ball just before it hits the ground. So kinetic energy will be according to principle of conservation of energy. K will be equal to U, and therefore this will also be 100 joules. What happens to the mechanical energy after the ball hits the ground and come to rest? Okay, your mechanical energy, now when it comes to rest, so that means the mechanical energy will get converted into some other form, okay, and the form into which, so whenever it is hitting and coming to rest, you will find there will be sound will produce, heat will be produced. So finally, the mechanical energy will get converted into the heat or the sound energy and the sound energy. Okay, the major portion will get converted into the heat energy. Okay, so this was question number 3. We move to the next one. Question number 4. Now here it is saying that a ski jumper, ski weighing 60 kg, stands at A at the top of his ski jump, moves from A, takes off his jump at B, calculate the change in the gravitational potential energy of the skier between A and B, and if 75% of energy in part A becomes kinetic energy, calculate the speed. So now what we have been provided with is here the weight is given as 60 kgf. Alright, so if we try to change it into Newton, this will be your 60 into 10 is equal to 600 newtons. Clear? Now, the ski jumper jumps from a height of 75 meter to a height of 15 meter. Alright? So the first part, what we have to do is, we have to find out the change in gravitational potential energy, that is delta U. Delta U will be your U1 minus U. This will be equal to mgh1 minus mgh2, or we can write down as mgh1 minus h2. Okay. Now mg means your weight, so we can write it as 600, and h1 minus h2, 75 minus 15. This is equal to 600 into this will be your 60. Hence 36,000, or you can also write it as 3.6 into 10 to the power 4 joules. So this is the change in the energy, that is from 75 meter when it comes to 15 meter. This is the change in potential, gravitational potential energy, and this will be considering that there is no loss of energy. Okay, now second part, it says that if 75% of this energy is converted into kinetic energy. So very simple, what it says, 75% of U, delta U, is equal to K. So we have to find out the velocity. So 75% means 75 upon 100 into 36,000. This will be equal to half m into v square. Okay. Now here we have to do one thing. We have to find out m. Now here we are not using mg. Weight we are not going to use. So let us try to find out m. So to find out m, we have already seen that W is equal to mg. So m will be equal to W by g. W was given as 600 and g is 10. So this comes out to be 60 kilograms. Clear? Now we put these values. So V will be V square is equal to 75 into 36,000 into 2 upon 100 into m. M is 60. So this will cancel from here. This will cancel from here. This will become 6. Alright. So V will be equal to under root 75 into 6 into 2. Alright. This comes out to be square. If you calculate the square root, this comes out to be 30 meter per second. Okay. So I hope this is clear to all of you. Now here in this case, you might have got confused that weight is given as 60 kgf and mass is 60 kg. So does that mean? No. Conceptually, if you see, weight is given in the gravitational unit, and since we are using the energy as a SI unit, so SI unit we use the normal unit. That is why we have first converted it into Newton, and then we have tried to find out the mass also in SI system. Okay, and therefore we are trying to get this. So, if you have any question, then we'll do the 5th and 6th also. Devesh, what happened? What you have written, I am unable to understand. Okay. You calculate it 56.25 upon 2, 56.25 upon 2. So that will be 56.25 plus 56 upon 0.25 upon 2. Okay. So then you calculate. Question number 3. Kinetic energy just before it hits. Yashita. So, part 2 it is asking you, in question number 3, in numerical number 3, part 2 it is asking you the kinetic energy of the ball just before it hits the ground. hits the ground means before it comes to rest. Okay. The rest when it will be having, we can say that it will not be having a kinetic energy. So that is why just before, so in order to say that there is no confusion for the velocity, so we are using the term just before it hits the ground. And concept remains same, the entire potential energy will get converted into your kinetic energy. See, whenever there is a change, if a body is falling down, always there is a change in kinetic energy, and this change in the kinetic energy is basically changing uh, at the molecular level. It will be changing its temperature. The collision will be more, and as a result, that is why we say that the kinetic energy, major portion of the kinetic energy gets dissipated in the form of heat. Now, heat doesn't mean that heat you can feel. It's not like it. You can feel only if its temperature is more than your body temperature. Okay, so it might be very very small amount of kinetic energy. Okay, but heat is always been produced. What is this 900 Harsh? There is some convention which we have to follow. Okay, and since the value certain time what happens, the value is too long and it becomes difficult to remember the values. Okay, say for example the speed of light. The speed of light uh, is your 3 into 10 to power 8 meter per second. All right, now if you try to remember in terms of its place values, it becomes difficult to remember. All right, similarly 10 to the power minus 6, say if you are writing down micron, okay, you will not remember it as 0.0000 and then the value. Clear? It is more easier to understand in the power of 10, and that is why we are writing down in the, we have got a scientific method of writing down, a scientific format of writing down the values. So I hope this is clear to all of you. For okay, okay, okay. I hope no other problem. I wish to. Harsh, Nishant, Rav Singh, Rahul, why you all have changed your font of your name? So I hope question number 4 is clear. Now we come to the next question, that is question number 5. In an hydroelectric power station, a hydroelectric power station takes its water from a lake whose water level is at a height of 50 meter above the turbine. Assuming an overall efficiency of 40%, calculate the mass of water which must flow through the turbine each second to produce the power output of 1 megawatt. G is taken as 10 meter per second square. Okay. So fifth we are doing. So in fifth, the height to which it has been taken is your 50 meter. Time it is taking is 1 second. The efficiency is 40%, efficiency of the machine. All right. G is given as 10 meter per second square. Okay. And the power in output, that is 1 megawatt. Megawatt will convert 1 into 10 to the power 6 watts. Clear? Now we all know that efficiency is equal to, in terms of the power input and power output, that will be power output upon power input into 100. All right. And once you know the power input, you are able to make out So let's try to find out the power input first. Efficiency is given as 40%. So 40, or I'll change the formula here and then put the values. So PI I have to find out. This becomes your PO upon efficiency into 100. PO is given as power output, that is 10 to the power 6 upon 40 into 100. When you solve this, okay, so here 15 and this will become 25. So we can write this as 2.5 into 10 to the power 6. Clear? This much watt. Now power input is equal to work by time. Here the work done is, because the water has been taken from the lake to a height of 50 meters, so work done is in terms of your potential energy mgh upon time. Okay, now we have to find out the mass. I hope up till here it is clear to all of you. Remember that whenever efficiency has to be calculated in terms of the power input and power output, it is power output upon power input into 100. Sometimes power output is given as useful power. Power input is the total power. Okay. So here now we will have to find out M. So the formula becomes M is equal to P into T upon GH. So P we get it as 25 into 10 to the power 5. T is 1 upon G is 10. H is 50. And if you solve this, you will get the required answer. That is 5,000 kg. Keep in mind all the values we are taking it in SI system. Okay. So here also you can get 10 to the power 4, 10 to the power 3, 25,000 by 50, and that you will get it as 5,000. I hope this is clear to all of you. I'll just do the sixth one. All these numericals you will be doing in your fair copy. Okay, so this exercise I have done all the numericals. All those who are writing down may be writing down. I'm doing the sixth one now. Sixth one says that the bob of a simple pendulum is imparted a velocity of 5 meters per second when it is at its mean position. To what maximum vertical height will it rise on reaching its extreme position if 60% of the energy is lost in overcoming the friction? Now, here again the concept is that kinetic energy is getting converted into your potential energy. But how much potential energy? In sixth, if you observe, it is 60% of energy is wasted in overcoming. So what is the used percentage? That is 40% is only useful. That means the entire of the kinetic energy, only the 40% of the kinetic energy is going to be converted into your potential energy. So we can write down as U is equal to 40% of K. Clear? Now U is equal to mgh. I'm not writing down the values here. Here we will take it from directly. 40% means 40 upon 100 into K is equal to half mv square. Half mv square. Now what we have to calculate? We have to calculate H. So m will cancel from here. Okay. So H we can write it as Two things will cancel. 40 upon 100 into 1 by 2 into V was given as 5 meter. So 5 is square divided by G. G is taken as 10. So now here if you solve all this, you will get it as 0.5 meter. Okay. So I tried to explain you what has happened. Okay. In next class we will be starting with the next chapter. Okay. But please be prepared for a test. I'll tell you the dates and the mode how we are going to do that. Okay. So from first chapter mostly. So if you have any question, you can ask. W is not equal to mgh. W was acha. W is equal to the potential energy we are trying to find out. That is why we are using, because the water in case of fifth question, the water is taken from the lake to that height. So that means it is getting converted into a potential energy, and that is why W is equal to mgh. Work done is equal to mgh. I hope Ashita is clear. Okay, Mayank, what happened? Group is open. You can put your question. Okay. So I hope up till here it is clear. In case if you have any problem, maybe due to any other circumstances, okay, please feel free to ask the question. Okay. And please let me also get an idea that you are doing the work. First question. First question, why you want to do like that? Okay, there are various ways. Okay, you solve it and put it into the group, and let me see what you have done, because here it is not so much of time. All right. So I hope everybody is doing their work. Keep on doing your work. Okay. And I hope all of you have already started leaving your class. I hope you all have forgotten that ticket. Before your teacher leaves you, you should not be leaving. So please. All right. Who is this with the number? Rahul. You send your detail. If you are not added, if you are added, then don't send it. Rahul, if you have not been added, then send your detail in the group or personally to me and find out the number. What happened, Ekansh? What to tell? Test will be taken starting from the first one only. First chapter only. And I will be giving you sufficient time and information beforehand. Okay. Let me first think of the modality. How can we do it? Okay. But definitely I am going to take a test so that I understand that you all also understand. And in case for internal, we can have these. Okay. So now I am ending the class.